where you are sharing your slides, and I'm going to start. Okay, welcome everyone. I hope you are enjoying this virtual conference. I'm Wendy Liu, Professor of Biostatistics at the University of Toronto, Canada. It is my great pleasure to chair this session sponsored by the Statistical Society of Canada, SSC. Before we start, I'd like to give a very brief introduction about the speaker, Professor Jemina Hamid. Jemina has been a faculty member in the Department of Mathematics and Statistics at the University of Ottawa in Canada since 2020. Prior to her current appointment, she held positions at research hospitals, academic institutes, and public health agencies. And she has extensive experience working with clinicians, practitioners, and researchers in interdisciplinary settings. During her undergrad training, Jemina was a double major in statistics and computer science at Addis Ababa University in Ethiopia, and she completed her graduate training in Sweden with a PhD in mathematical statistics with specialization in multivariate methods. Her research focus has been around methodology development and applications, and she has published extensively in both statistics and biomedical journals. I'd like to mention that Jemina was the inaugural chair for the SSC Committee on Equity, Diversity, and Inclusion, and she led the development of the committee's mandates and terms of reference. She is continuing to be an active member of the EDI committee for the SSC. In the interest of time, for more information about Jemina's research interests, publications, and her leadership roles, I will refer you to her website, which I will send through the chat shortly. Her presentation today is about the title is rare, so I will not repeat everything related to her research work that is ongoing. As a reminder, I'd like to ask you to send your questions through Q&A or send your questions through the chat, and then I will read that on your behalf. Okay, that's all. And over to you, Jemina.
Thank you very much, Wendy, for the invitation and for the nice introduction. Thank you, everybody, for organizing this. And I'm happy to be here and share at least an overview of multivariate bilinear models, and I will highlight some of our contributions as well. So I will talk a little bit about linear models first, multivariate linear models, and then go to GMANOVA, multivariate analysis of variance model, which is a bilinear projection, and give you some highlights of some methodological advances. And if I have time, I will speak briefly about high-dimensional application. So everybody, I'm sure, knows about multivariate data. Multivariate data, if we have multivariate outcomes, for example, from K groups, p-repeated measurements, it could be the same outcome measured p times, or different outcomes, p different outcomes measured from each individual across k time points. Obviously, we will model it as a multivariate analysis of variance model, where we have y equals bx plus e, where e is the error term, which usually we assume to be multivariate normal distributed. The columns of E would be independently and identically distributed with multivariate normal distribution. Of course, I could have added more covariates, but I would like to just present it at a simple level. So I'm only including indicator variables indicating which group the individuals are coming from. Basically, that's an extension of ANOVA to MANOVA. And this tells me where the individuals are coming from. So we call it the between individual design matrix. Obviously, the beta matrix tells me the mean differences between the groups. And our interest is to estimate the mean differences or the means themselves. So the model usually is set up, as I said, as a multivariate model. Y is equal to bx. We could use either least square approach by minimizing the difference between the observed and the estimated value, or it's the same thing as maximizing the likelihood under the normality assumption. So under normality assumption, if I maximize this likelihood or minimize the error sum of square and cross product matrix, I would get the same results, which the traditional B hat Y multiplied by this matrix. And if I have Y hat, which is the estimated mean, in this case, because I'm interested in MANOVA, the estimated mean would be the projection of the observation matrix on the column space of the design matrix. So all of us are familiar with this expression for Y hat. The residuals would be Y minus Y hat. Obviously, if I project Y on the column space of the design matrix X, I get Y hat. If I project it on the orthogonal space, I will get R, the residuals. As you can see, I can simply present it into two spaces, one of them representing Y hat, the other one representing the residual. If I take the cross product of Y, Y prime, R, R prime, I will get, the decomposition, the usual decomposition of decomposition of the space of variation of the observation Y. So this is what we call a decomposition of the sum of squares around the mean. So R prime is basically the product of this expression. Because of idempotency of the matrix, I will have Y times the same projection matrix, the orthogonal projection matrix times Y prime. So that's basically, in this case, in MANOVA case, it becomes the numerator of the estimator, the sample covariance, the estimator of the population covariance matrix. That means the sample covariance matrix would be R prime divided by n minus 1. So that's basically an overview of the MANOVA model, its estimators, the mean estimator Y hat. Y hat is the estimated mean, and the residuals and the estimated value for the variance covariance matrix sigma. Now I'm going to take it a little bit further and say, let's now focus on one outcome, and P repeated measurements are taken from the same outcome. Instead of now modeling unstructured mean, like the previous one, I'm going to structure the mean. That means there is going to be a relationship between the outcome and time, or it can be dose response curve. So if I'm interested in the dose and response or time and the outcome, then I will have a structure. In this case, I have the relationship between the outcome and time, almost like a linear function, but it doesn't have to be linear. So if I now model the mean trajectory over time for each group, in this case, I have two groups, but it doesn't have to be two groups. It can be K groups. If I can model the mean trajectory over time using a polynomial, then I can add now linear restriction on B. If I add linear restriction on B, which means I will have something that's measuring the structure of the mean, the Z will be measuring the structure of the mean, and X would be the same design matrix I talked about before, telling me which individuals are coming from which group. So because of these involvements of two design matrices, we call the GMANOVA model a bilinear regression model. So you will see later on in a couple of slides, it also involves bilinear projection. I am quickly going to talk about now the maximum likelihood estimators without talking too much about it. So if I talk about the likelihood estimator, instead of now the mean difference, it will become the coefficients of the polynomial. So the estimator is estimating the coefficient of the polynomial, but Y hat would be the estimated mean trajectory. So if this was the observed mean trajectory, Y hat will give me the estimated mean trajectory. As you can see, the estimated mean trajectory is a projection of Y on both sides by two projection matrices, Px and Pz. Pz is a projection projecting it on the structure of the mean, the time component, and Px is projecting it on the design matrix that is X. As you can see, S is involved in the projection of Z with respect to Z. The reason being there is correlation. Here we don't have any correlation, so we don't have a weighted projection, but in this case we have weighted projection. And as you can see, the projection matrix is not orthogonal because it's not symmetric, but this one is orthogonal. So we can talk a lot about the orthogonality, the non-orthogonality, and the relationship between the different parts of the residuals. So one of our contributions, earlier contributions, is trying to understand these projection metrics, because Y is in the middle. It's difficult to understand the projection metrics. So what we did is trying to use the VEC operator and see if we can simplify the projection into a linear projection, but that linear projection will have now a chronicle product. That's one of our contributions. Using the chronicle product, then we will be able to understand especially the R space, the residual space, in addition to the design space, which will give us Y hat. So again, you can see that it's bilinear projection. Before I mentioned that we have two design matrices. It's a bilinear model leading to a bilinear projection, one of them weighted and one of them unweighted. So if you compare it to the MANOVA model, you could see the difference between the projections in MANOVA and the projections in GMANOVA. So our contribution, as I said, is quantifying the space created by the two design matrices and then their orthogonal complement, so that I can understand what it means, what the orthogonal complement is. By understanding the orthogonal complement, we were able to break down the orthogonal complement. And one of the reasons is that because R is difficult to understand, if I say Y minus Y hat now, because Y hat is this complicated expression involving S inverse, Y minus Y hat becomes a difficult expression for me to understand from distribution perspective, from the property perspective. For example, if I want to use the residuals from the analysis of longitudinal data, we run into problem because we don't know whether they are multivariate normal or not. If we don't know whether they are multivariate normal or not, we are not going to be using them to check the multivariate assumption. So I'm assuming that somebody will tell me, will check the chat and let me know if it's a question. So I'm going to go on with my presentation. So what we have here now is the projection with respect to the residual space broken down into pieces so that I can understand the property of the residuals. So here I can show mathematically that R1 plus R2 gives me the same residual as the MANOVA residual. That means it's a linear function of Y. That means I can check the normality assumption using only R1 and R2. We can also mathematically show, you can find it in these papers, we can also mathematically show that R3 is the difference between the mean. You could see the first column is the mean, the observed mean, because it will be a projection on this space, the one that I'm highlighting in here. So the projection here in this space will give me the mean. So if I project that mean, I will get that mean in the column space of Z. I will have the estimated value, but R3 will be what's left unexplained by the projection with respect to Z. So I can show mathematically that R3 is a difference between the observed and the estimated mean. That means I can check model fit using R3. And from our understanding of this residual decomposition, we were able also to show to motivate a hypothesis test for the mean parameters of the growth curve model. And this hypothesis test that I am presenting here, it's not just from a conceptual understanding of the residuals and the design space, it's actually the result of likelihood-based approach. The only input we put in the likelihood is that we put it as a sequential testing approach, whereby we estimate the covariance matrix first from the independent part of the residual space R1 plus R2, and then we feed it to the likelihood so that we can get the ratio of the estimated likelihood. That gives us this test, and the simplification of the test is given in our paper in 2011, that you can see is an extension of the famous Lowry-Hotelling trust test. And we showed the behavior of the test, its optimality with respect to the null distribution and with respect to the null distribution and alternative distribution. This is what I talked about. R1 plus R2 is nothing but S, where S is a numerator of the estimator of the covariance matrix. The sample covariance matrix will have S as a numerator, which means I can talk about the variation around the mean, which I can talk about also R1 plus R2 being normally distributed. Because it's normally distributed, I can use it as a value that I can check the normality assumption. But traditionally, what we do is we just use the ordinary residuals R, the entire R space, to check the normality assumption, which is wrong. Let me now extend it a little bit again. We started from MANOVA, we went to GMANOVA, and GMANOVA, as I said, is if I have a trajectory over time or a dependency in the mean or a structured mean, I can put that in a design matrix called Z in order to be able to account for the relationship between the outcome and time, while, for example, comparing the groups. I can compare the groups using hypothesis testing while incorporating the structure over time. What about if I have now different structures over time, one of them linear and one of them quadratic, or whatever? I may have multiple clusters or multiple groups, and each of them may follow different dependency, time dependency, or mean structure. In that case, the GMANOVA model doesn't help me, so I go to the extended growth curve model. For the two groups I showed you here, I can model it as additional linear restriction, so that I can impose on two design matrices with respect to the between individual design matrix and two design matrices with respect to the within individual design matrix. If I have multiple clusters, more than two, I can model it using the extended growth curve models that I'm giving here. Again, it boils down to understanding the design space and the orthogonal complement. We were able to show that the design space remains the sum of two chronicle products, the Coleman space of a matrix that is the sum of two chronicle products, which we can change into tensor product space using the theory of linear algebra. Once I understand that, we could take the orthogonal complement. If I call everything inside here P, a projection matrix P, then I can represent the matrix generating this Coleman space I minus P. So the orthogonal complement would be I minus the matrix inside here. By understanding that, we can actually start understanding the design matrix and the orthogonal complement, which I put here just for simplicity purpose. We can first induce nested subspace condition on the axis and on the z's. We showed that it breaks down into different nested subspaces, and then this nested subspace we can decompose into different residuals. I'm showing the minimum number of residuals we have, but I could have, for example, drawn a line in here as well. So I could have broken it down a little bit more. We could also use the design space and again, break it down into different areas mathematically. I mean, using linear algebra concept, the theory of linear algebra, we can mathematically break down the space generated by the four design matrices and the residual space. That helps us understand which residuals I can use, for example, for the normality assumption. I can use this residual R1 plus R2 for the normality assumption because it remains the same residual that we saw in MANOVA, and the S we saw in corresponding to the S we saw in GMANOVA. This one I could check the quadratic, for example, if I assume quadratic polynomial for the second group, I could check that component of it, and this one, sorry, the linear component of it, and this one for the quadratic component. If I want to check the entire overall fit of the model that I fitted for two clusters in the extended growth curve model, I can use R3 plus R4, etc. So our understanding of the residuals also lead us to develop hypothesis testing involving longitudinal data that are clustered with different trajectory over time, different shape of the mean trajectory over time. So I will just briefly give an example in high dimensional data. We extended also our work to high dimensional data using both frequentist and Bayesian method. And that high-dimensional data will have, for example, thousands of genes, and then longitudinal measurements taken on a specific outcome, or longitudinal measurements taken, for example, it could be gene expression on each of the genes. So you have longitudinal outcome, which can be also P can be greater than N, singularity at a gene level, and it can be also thousands of genes. We can use the growth curve model or the GMANOVA model or the extended growth curve model or the extended GMANOVA model, either, for example, to do gene filtering. That means removing genes that are not expressed over time with a flat profile, or we could rank the genes with respect to their differential expression between, let's say, case and control. So what we did here is I think gave you an example from the breast cancer data that we had. We analyzed the data. We have more than 20,000 genes, and the analysis is gene by gene. However, the analysis involves longitudinal data at a gene level. And I'm just showing you the critical values that we generated for the corresponding test statistic that allows me to see if the genes are expressed at all. That means we remove the genes that are with flat profile. So to summarize, it's a quick run of a presentation of MANOVA, GMANOVA, and extended GMANOVA. MANOVA can be used, it's a multivariate linear model. It can be used to compare vector of means across different groups. GMANOVA extends MANOVA by allowing a structure to be induced in the mean. It's basically a natural extension of the MANOVA model. Mathematically, you can put a linear restriction on the parameters B in order to get a GMANOVA model. Conceptually and from application perspective, what we are doing is we are incorporating the relationship between time and the outcome while still comparing if there is any difference between the two groups. So because we're incorporating more information that is contained in the data, it gives us better estimation and better hypothesis testing, better statistical power, because we are maximizing the information. Because of the explicit nature of the estimators, it allows us to extend it to high-dimensional data. It allows us also to understand the design space and the residual space, which prompts extensions for example, non-normal data. We have extended our work to non-normal data by incorporating, by allowing the error terms to have a distribution other than the multivariate normal distribution. One of our work, for example, assumes the multivariate skewed normal distribution, which is more flexible than the multivariate normal distribution. Of course, I mentioned it before. It involves bilinear projections instead of linear projections. One of the projections I mentioned is weighted, which is traditionally weighted from maximum likelihood procedure, weighted using the inverse of the sample covariance matrix, which creates sometimes a problem for us because of singularity or because of sample size, for example, being small and it's not properly estimated, the covariance matrix not being properly estimated. In that case, we can allow iterative reweighting of the covariance matrix so that we get a better estimation. We have done that extension as well. The extended growth curve model also allows flexibility of clustered longitudinal data to be modeled, unlike, for example, the GMANOVA, the MANOVA, or even unlike the linear mixed model in general. So these are my collaborators. Thank you for your attention. I went fast on a very deep and rich topic, but I hope you get a sense of at least how the models are connected to the MANOVA model. Thank you again for inviting me, and happy Women in Statistics and Data Science Day. If I knew purple was the color, I would have used a color purple in my congratulations. So thank you so much for your attention. I would love to answer some questions.
So are there questions for Jamila? And audience, if you are not in the panel, you can always write your questions in the question answer, and then we can read it for Jamila. So while that's going on, Jamila, I actually have a question for you because this is a topic I'm super interested in.
Yes.
And my question is, you said we can go from normal to non-normal. What about the scenario? Can this be extended to generalized models? Like if I have a binary model or ordinal model, so which is not the general linear model, but the generalized linear models? Just because the problem comes, and it's a much harder problem there. But, the idea of breaking it up into 4 and then looking at, the errors, looking at the residuals is very interesting. I'm just asking, have you thought about it?
Yes, I was scrolling up actually to say that unfortunately the assumption is there is a functional continuous relationship between the outcome and time, or the outcome and, let's say, dose and response. So it assumes continuous outcomes. So because of course, mathematically, so without talking about, for example, the relationship, the smooth relationship, the polynomial relationship, we can talk about mathematically, how could we induce a structure in the mean? So the overall concept is inducing a structure in the mean. If there is any structure on the mean, that means if there is any relationship between the repeated measurement and time, it can be induced through additional design metrics.
Okay.
But it wouldn't be using a polynomial function, because a polynomial function is a continuous function, so it's representing a continuous relationship between outcome and time.
Okay. Yeah, I think there are some, I think there are some other ways maybe we can look at it, like especially like if you don't have, say, binary data, but let's say you have like ordinal data, and then you have, and there is a relationship with time. We know there's a relationship with time. It's some sort of a growth type model. Then,
Yes.
you can impose the curves, but use the technique to break down the, the total sums of squares into those partitions.
Yes. Any linear restriction, if you put MANOVA, can be used when you have non-continuous data, right? Mm-hmm. So basically, mathematically, what it does is you have B, you put a structure on B. It may not turn out to be the same structure as I was showing, but you're just putting linear restriction. So you are maximizing or minimizing the likelihood or minimizing the error, sum of square and cross products. But the restriction you impose is on the parameters of the mean.
Yeah. Okay.
So you could still do that.
Okay. And I will actually reach out to you because I'm doing a problem fairly similar, but this kind of projection would really help, I think. Okay. Other questions? If not, let us thank Jamila again, and we will let Teresita, you can maybe unshare so that, and
Yes.
And
thank you so much.
Again, people, if you have questions for Jamila, you can directly contact her, because we are not having that much time between our sessions for actual questions. So, Jamila, is it okay for the people to contact you?
Yes, I'm putting my email.
Okay. Yeah, and so if you can reach her directly for access to, because there is one question here, if people can have access to slides. So, okay. Yes. So just reach out to Jamila and she can make that available for you. Okay.
Thank you very much again.